Hello, my dear friends. I'm Shubham from Learnohub, the free learning platform where you can study physics, chemistry, maths, biology absolutely for free at learnohub.com. So then, let's start. So friends, in this video, we are going to see your ICSE class 9th, chapter number 6. Okay, so far we have covered up 5 chapters. And in this chapter number 6, the study of first element, hydrogen, we have also covered quite a lot of concepts in the previous 2 videos. So if you would have missed those 2 videos, you can go back and watch them. Okay, and then come back to this video because we have studied a lot of things, okay, of this chapter, and you would be able to correlate and understand it more easily if you would go back and watch those videos, learn those concepts and come back to this video. Fine. Also, along with the concepts, we will also see questions so that you would get a hold, or you would be able to think whatever we have studied. Okay, out of those things, some of those things you could see if you can use and answer the questions. Okay, so without wasting much time, let's start and let's rock. Okay, so we have seen the reactions of some metals with water, right? So the water was cold enough, the water was boiling, and then we have also seen some reactions of metals with the steam as well, right? And the activity series. So all these things in the previous video, we have gone through these reactions. Now, going ahead, we will see the reaction of now steam with a non-metal. Okay, so enough about the metals. Now let's see the reaction of steam with a non-metal, and here we are going to see the reaction of steam with carbon. Okay, so in this reaction, okay, where the carbon is reacting with steam, we produce hydrogen, and this process is called as Bosch process. Okay, so we are going to see how this Bosch process works and how we get hydrogen through this Bosch process, right? So you have got a fair idea that what we are going to take is carbon and steam, and we are going to produce hydrogen. Now let's see step by step this process, okay, how we are going to end up producing hydrogen, which we want, like very much with that attraction towards that element we are having, okay, hydrogen, because now we are now fed up with the reactions because there are some or the other demerits of a particular reaction, right? Whichever we have seen till now. Okay, there were some reactions of metals which were quite favorable for us to produce hydrogen. Okay, but let's see a industrial process, okay, with the help of which hydrogen is produced on a commercial scale. Okay, so Bosch process is used to produce hydrogen on large scale. Fine. So the step 1 of this process is to produce a very interesting called gas, okay, which is called as a water gas, okay, or we call it as syngas. Okay, now this, what is this water gas or syngas? It's very easy. Okay, what we have to do is we have to take carbon, we have to take steam. Fine. So I have just taken carbon, okay, and then I have taken steam. Okay, fine. And what happens is this carbon reacts with our steam, okay, and it produces carbon monoxide gas and hydrogen gas. Okay, so how can you just remember this thing? See, carbon, water, okay. Now here this carbon and this oxygen, you just think in this way, okay. The reactions don't take place as like the way I'm saying you, okay. I'm just giving you a trick to remember the things, okay. So you can just remember in this way, carbon is pairing up with, or carbon is telling oxygen, let's shake our hands, and they are combining to form carbon monoxide. So one carbon, one oxygen combined to form carbon monoxide, and then what is remaining? Remaining is just hydrogen. So okay, so carbon monoxide and hydrogen is produced, and this mixture of two gases is called water gas or syngas. Clear? Now along with this, the reaction is such that, okay, it is absorbing a huge amount of heat. Okay, it is absorbing a lot of heat. Okay, forget about the huge amount, but it is absorbing heat. Okay, it is an endothermic reaction. So what I can write is, now we know how to write endothermic reaction, okay, or how to show the heat aspect in the endothermic reaction. You can just show in the reactants plus heat here, okay. In the reactant I can show plus heat, right? But if I wish, I can bring this plus heat to this side and then it would become minus heat, okay. So I can write anyway, this minus heat can be written here as plus heat, because minus would change to plus when we would turn the side, okay, when we would change the side. Fine. So this is showing that the reaction is endothermic. Fine. Understood? You can write this minus heat here also, okay. Carbon plus steam plus heat gives carbon monoxide and H2. Now when we write here plus heat in the reactant side, it is an endothermic reaction because heat is being absorbed. We have studied all those things, right? Now the thing here is, I have told you the reaction, okay, but how the process is taking place. So we have to react our steam with carbon. So what we take is coke, okay. Now don't go and jump to that coke, okay, just like you are drinking beautiful sip of coke along with burgers and all those things. No, not that coke. No, I'm not talking about that coke. I'm talking about a different type of coke, which is a product, which is a coal product simply, okay. When we burn coal, we get coke, okay. You can remember in this way. And this coke mostly contains carbon, right? So that's the reason we are taking coke, because we want our carbon to react with steam, and coke mostly has carbon, okay. So carbon reacting with steam. Now carbon here is reacting with steam, but how we carry out the reaction, okay, not just like this. We have the temperature, we maintain the temperature of 1000 degrees Celsius, okay. So this much temperature we have to maintain, okay, for the reaction to take place. And how it is done, we pass, okay, the steam, okay, over our coke. Fine. So steam is passing over the coke at this temperature, at this very high temperature, 1000 degrees Celsius. That's it. So these are the conditions. This is only condition here for the step 1, that is we have to maintain the temperature of 1000 degrees Celsius. That's it. And we have to pass the steam over the coke. So what would happen when we pass the steam over the coke? The carbon, okay, coke is mostly made up of carbon. So carbon from the coke, okay, it would react with the steam. It would produce carbon monoxide and hydrogen gas, which is our water gas or syngas. Correct. Now the next step would be, you are guessing right, it would be involving this carbon monoxide and hydrogen gas, right? So let's see what the next step is. Now in this step, we are going to use our syngas to produce more hydrogen. Like we humans have the tendency, we are not happy till we get the most of that thing, right? That's the reason you may be watching the video, because like you want to learn the concepts in a very crisp manner, or very quickly, or in an interesting manner, or in a simplified manner, where we come into, okay, we make the learning as simplified as possible. So that's our motto, to make learning as simplified as possible. So humans also tend to get the most of the things, okay. So they think that, can we produce more hydrogen, or can we generate more and more hydrogen still, okay, still after step 1 also, still can we generate more hydrogen? And in this way they thought, okay, humans thought, and then they designed this step 2. Let's see what this step 2 is. So in this step 2, okay, here we are going to use our syngas itself, okay, and from this syngas we are going to generate more hydrogen. How? Let's see. So this syngas, carbon monoxide plus hydrogen, okay, I'm going to treat it with now excess of steam. Now I would take up this, carbon monoxide and hydrogen, and then I would again mix it up with the steam, okay. So here carbon monoxide and hydrogen, okay, and then this thing I'm going to mix it up with steam, okay. Just diagrammatically I'm trying to show you. So steam, here the reaction here is, okay, this is our syngas. I'm not going to write it again and again. So carbon monoxide and excess of steam would result us into carbon dioxide and again hydrogen, okay. So how to remember this thing? See, for example, this carbon monoxide is picking up this oxygen with it, okay. So it formed carbon monoxide, carbon and one oxygen, and again one oxygen. So carbon and two oxygens, so carbon dioxide. CO2 is carbon dioxide, right? So CO 2. Then what is remaining? 1H2 and 1H2. So 2 H2s are remaining, right? So CO2 and 2H2. That's it. Okay. Now you can see here in this reaction also no need to balance the reaction. It's already balanced. Here also no need to balance the reaction. It's already balanced. Okay. Now see, I have just told you the trick to remember the products. Okay. The reaction will not exactly happen the way I'm saying. Okay. It's means how have I told you that carbon monoxide would pick up this oxygen and it would form carbon dioxide. Okay, that's not always the case. Okay, maybe sometimes carbon monoxide would behave in some another ways as well, not in this reaction but in some another reactions. Okay, I'm just trying to tell you the way in which you can remember the products. Okay, it's a simple trick. So what I follow is I'm going to tell you. Okay, so you can either remember in this way that carbon monoxide, okay, sorry, in this way that the syngas reacts with the steam and it produces carbon dioxide and hydrogen in this way, or if you find useful my technique, you just write the reactants and then remember the way, the trick which I'm telling you. Carbon monoxide and 1 oxygen it picks up, it forms carbon dioxide and then 2H2. So carbon dioxide and then 2H2. Fine. So you get the right products as well. Now here what has happened is, see, our steam, okay, it's having H2O, right? But the oxygen is being picked off, right? Means it has been removed from the steam, and then we get hydrogen. Okay, so somewhere or the other place you can see that the steam, though it is in excess, okay, what is happening here is in the steam, that is water, the oxygen is being removed off. Okay, so I'm telling you here just that whenever the oxygen is being removed, it is called as reduction. Okay, so we will learn it in quite more details, but for now you can just remember in this way that since the oxygen from here it is removed, see, carbon monoxide is taking up this oxygen, right? So it is forming carbon dioxide. Okay, so in this way you can understand. So since the oxygen is being removed from the water, right, carbon monoxide picking up the oxygen, so oxygen is removed from this water, so and it is resulting into the formation of H2. Okay, the hydrogen is getting deprived of oxygen. Okay, so this is a reduction, removal of oxygen, reduction. So here reduction is taking place of steam. Okay, so steam here it is reduced, fine, steam here it is reduced, and what is formed? Okay, H2 is remaining, right? After this oxygen is removed, the H2 is remaining, right? So this H2 is formed. Okay, so steam is reduced to hydrogen, right? Steam is reduced to hydrogen, H2. Clear? Fine. Now moving ahead. So in this reaction, it doesn't take place like this, okay, like this only. It requires some temperature conditions, some catalyst as well as some promoter as well. Okay, so what temperature it requires? Okay, this reaction takes place at 450 degrees Celsius. Okay, the catalyst it requires is Fe2O3, okay, ferric oxide, and okay, this is the catalyst, and you also require a promoter here. Okay, I will just erase this thing so that I can accommodate. So here steam, fine, excess, okay, and here the promoter is Cr2O3, chromic oxide. Okay, so this is the catalyst, I'm just writing C here, this is the promoter, I'm just writing P in front of it. Okay, now catalyst you may be knowing, it just speeds up the reaction, fine, and promoter is someone which is like you can just imagine that it is pushing the catalyst, okay, pushing the catalyst to increase the speed of the reaction. In short, promoter simply increases the efficiency of the catalyst. Okay, it makes the catalyst more efficient. Okay, fine. So it pushes the catalyst to work more efficiently in this way. You can just remember. Fine. So what are the conditions? I have explained you. And now what is the process? So how the step 2 is carried out? What I have told you is this carbon monoxide and hydrogen gas, that is the mixture of these two gases, is syngas. This gas is mixed with the excess of steam here, and fine, and this mixture, okay, this mixing takes place under these conditions. The temperature is maintained at 450 degrees Celsius, okay, and yes, this mixture, okay, at 450 degrees Celsius is passed over the catalyst and the promoter, you can see. Okay, so catalyst, promoter, okay, it is passed over the catalyst and promoter. Find this mixture. So what it does, the catalyst and promoter speeds up this reaction. That's it. And we get products as carbon dioxide, and again we generate hydrogen. Okay, so from step 2 also, so from the product, okay, hydrogen means, so from the syngas we are again generating more and more hydrogen. Correct? How? By reducing the steam, fine, to hydrogen. Very easy. So you can just remember the process. Automatically you could get the hold of the things. Okay. What I mean was not remembering the process. You just understand the entire process, how the things are taking place. Automatically you would remember the things. Okay. So bacho, let's start with the Bosch process third step. Okay. So the third step is not like we are again going to increase the yield of hydrogen. Okay. No. We are simply going to remove the things which we don't want, which are now present along with hydrogen. You would say, sir, what is present now with hydrogen? Okay, now you can see in the step 2 here, carbon dioxide, this nasty guy is present with hydrogen, right? So we need to remove this carbon dioxide from the, or we need to remove this carbon dioxide from this carbon dioxide and hydrogen mixture, correct? And then only we will get completely hydrogen, means then only we will get pure hydrogen. Fine. Okay, so first, how to remove this carbon dioxide then? So there are like quite 2 easy methods to remove the carbon dioxide which has been obtained as a product along with the hydrogen in the step 2, which is simply, first we can pass the mixture of carbon dioxide and hydrogen, okay, through water. Wow, superb. So if I'm taking water here, okay, and I'm passing this mixture through this water, what would happen is, okay, now I'm drawing a very rough diagrammatic representation of this process. Okay, don't take it as a means like actual representation of the process. So when I would pass this mixture into this water, okay, under like high pressure, almost like 30 atmosphere pressure is there, and at this pressure the mixture is forced into the water. Okay, it's passed into the water, and the carbon dioxide from this mixture, okay, it dissolves in the water. Okay, and what remains is then simply hydrogen. Correct? So carbon dioxide gets eliminated by this method. The another method is quite very easy. We have to just pass this mixture, okay, same, this carbon dioxide and hydrogen mixture into caustic potash solution, that is KOH solution, right? Now what KOH does is simply KOH reacts with carbon dioxide to form potassium carbonate. Fine. So in this manner carbon dioxide gets eliminated, clear, and what remains is hydrogen. So here KOH reacts with CO2 and it forms K2CO3 and H2. You can balance the reaction later on, okay, as your wish. Fine. So this is how we are going to remove carbon dioxide, okay, from this carbon dioxide hydrogen mixture which we have obtained as a product in step 2. Okay, but there is also one more thing which we need to do is, when we are passing this carbon monoxide and hydrogen gas mixture, that is the water gas mixture, okay, and we are also, okay, making this water gas, okay, or treating this water gas with excess of steam over this catalyst and promoter at this temperature. So whatever water gas, right, and or we can say that whatever water gas and the steam, okay, which we are passing over this catalyst, clear, reacts, it's fine, it would give us carbon dioxide and hydrogen. But what about the unreacted carbon monoxide? Okay, so what we do is, this mixture of syngas and steam, okay, as we are passing through the catalyst and promoter at this temperature, we get this products, but similarly we pass this, okay, mixture, okay, so the mixture which is giving us this product, after it is giving us the product, the same mixture, okay, this same mixture, you're trying to understand, okay, we are passing this syngas, that is water gas mixture, and the excess of steam over this catalyst at this temperature, catalyst and promoter at this temperature. But all of it, okay, won't react to give us carbon dioxide and hydrogen. Okay, some of it may remain unreacted, right? So if some of it is remaining unreacted, so what we need hydrogen from it also. Understood? Why should we leave the hydrogen which is still, okay, which is not reacted in the step 2? Why should we leave that hydrogen? For that purpose, what we do is we pass this unreacted mixture of syngas and steam, okay, into the ammoniacal copper sulfate solution. Okay, so here I'm just writing ammoniacal cuprous, sorry, not copper sulfate, cuprous chloride solution. Okay, sorry, I'm like used to saying copper sulfate so much that I just used the copper sulfate. I said copper sulfate instead of cuprous chloride solution. So what happens is the carbon monoxide, fine, okay, it gets combined with the cuprous chloride solution, okay, and this cuprous chloride, CuCl, now you can derive the formula. Cuprous means the copper ion having 1 plus charge, okay, or the radical of copper having 1 plus charge, and chloride, you know, 1 minus, so Cu1 plus Cl1 minus, it is CuCl, simply the way we use the crisscross method and derive the formula. So you can derive the cuprous chloride formula in the exactly same manner. So this carbon dioxide and cuprous chloride, okay, and this water, okay, so this ammoniacal cuprous chloride solution, okay, what it does is it picks up this carbon monoxide and it forms like this CuCl dot CO dot, and here we are going to take 2 water molecules, so 2 water molecules. So this is somewhat the product which is formed, and this is what, not somewhat, this is the product which is formed, okay, CuCl dot CO dot 2H2O. So in this manner carbon monoxide is removed, okay, from the unreacted, okay, steam and syngas mixture. Fine, clear. So from that also we have recovered the hydrogen gas, right? So the step 2 reactants, in step 2 reactants we are having hydrogen gas and we are recovering in this manner, okay, by eliminating the carbon monoxide or by removing the carbon monoxide. Fine, how to remove the carbon monoxide? Simply pass the unreacted mixture, okay, of the reactants in step 2 through ammoniacal cuprous chloride solution, and then copper and then carbon monoxide is removed. Clear? According to this reaction. And so we have completed the entire Bosch process. Fine, we have understood on on how the hydrogen is produced on large scale, right? But let's move on to the next method of preparation of hydrogen. Now we have studied the preparation of hydrogen with the help of water, right? Now let's study the preparation of hydrogen using acids. Okay, I'm just joking. I just pronounce the word acid like this, okay, but it's like, I know you all know it's acid, but for fun only, okay, acid. So this acids, okay, what we do is we use dilute acids. Now we will start using dilute acids, okay. If you're not able to see, I'm just writing here dilute, okay. Now which dilute acids we are going to use? This 2 dilute acids, sulfuric acid and hydrochloric acid. Fine. Now here we are going to treat again, what we are going to treat? Metals. Fine. So we are going to take up metals and we are going to make them react with dilute sulfuric acid or dilute hydrochloric acid. Now a very important thing you need to remember here is which metals will react with this dilute sulfuric acid or dilute hydrochloric acid? The metals which are above, okay, hydrogen in the activity series. Fine, you need to remember this thing, okay, very logical thing. So these metals, okay, when they are treated with sulfuric acid or hydrochloric acid, they result into their metallic sulfates. Fine. If they are reacting with sulfuric acid, they would result into metallic sulfates. And if they are reacting with hydrochloric acid, it would result into metallic chlorides. Very simple. Along with, now what we are interested in producing hydrogen. So that's it, along with release of hydrogen gas. Fine. Okay. So this would be the general reaction which you need to get into your head, and then your job is done. Fine. So which metals reaction we are going to see? We are going to see the reactions of magnesium, fine, then aluminium, zinc and iron. Very clear. So what we will do is we will first see the reactions with dilute hydrochloric acid, and then we will move on to see the reactions with dilute sulfuric acid. Very simple. So what would happen when magnesium reacts with, I'm just writing here above only, okay, dilute. Okay, now now here I'm not again going to repeat for each and every element the word dilute. I'm just simply writing dilute here at the top. Hydrochloric acid, aluminium, hydrochloric acid, zinc, hydrochloric acid, iron, hydrochloric acid. Now what would be the product? What would be the product? Magnesium would react with hydrochloric acid. It would form magnesium chloride and hydrogen gas would be released. Aluminium would react with hydrochloric acid, forming aluminium chloride, AlCl3, whose formula is AlCl3, and hydrogen. Okay, magnesium chloride formula is MgCl2. Zinc would react with hydrochloric acid, forming zinc chloride, ZnCl2 and hydrogen. And the same way, iron would react with hydrochloric acid to form ferrous chloride, okay, FeCl2, releasing hydrogen gas. Now you can balance the reactions, quite easy job. Okay, fine. Now in the same manner, they would react with sulfuric acid, correct? So magnesium, again, magnesium, aluminium, zinc, iron reacting with dilute sulfuric acid. Okay, so it's dilute. I like to call it as dilute, whatever you can call. Just you have to make your learning more fun. Okay, so now here what would happen? All of them would definitely give us hydrogen gas. Now why I'm saying this? Because you know the 4 elements which we have picked up to study the reactions with hydrochloric acid and sulfuric acid, or as an example for the reactions of metal with sulfuric acid and hydrochloric acid, you know these 4 metals, okay, like magnesium, aluminium, zinc and iron, you can figure out that they are all above hydrogen in the activity series. They are all above. Okay, so they would definitely react with these 2 acids. Clear? We all know that, yeah, at the top it would be potassium, then sodium, right? Correct? Potassium, sodium, and then calcium, magnesium. Fine. So magnesium is quite above, and then after that aluminium, and then it is zinc, and then zinc, and after zinc, okay, for magnesium after aluminium, and then zinc, iron, and then we all know nickel, tin, lead, and all those things, and then we come to hydrogen. So all these metals are above hydrogen. So that's what I wanted to show you. Okay. So they would definitely react with dilute hydrochloric acid, dilute sulfuric acid, and they would form, now here they would form metallic sulfate. So here magnesium reacts with sulfuric acid, forming magnesium sulfate, MgSO4, okay, and hydrogen gas is released. You can balance the reaction. I will definitely tell you this is exactly balanced reaction, okay, because see, this is my trick to see whether the reaction is balanced or not. See, magnesium sulfate is formed, so entire Mg and 1s and 4 oxygen are removed. So what is remaining? Hydrogen gas. So magnesium sulfate and hydrogen is formed. Magnesium sulfate and hydrogen is formed. Exactly balanced. Correct. So aluminium and sulfuric acid. Now this would form aluminium sulfate. Now here aluminium sulfate's formula would be Al2. Okay. SO4 thrice. Now how I could make it out? Okay, simply by crisscross method. So you can use the crisscross method in your brain and you can get the formula. Fine. Sulfate is having 2 minus, therefore it would come here 2. Aluminium is having 3 plus, it would come here 3. Clear? Fine. So now here zinc sulfate, similarly ZnSO4, and then iron sulfate, it is FeSO4, ferrous sulfate would be formed along with the formation of hydrogen. Okay. So if they are not balanced, you have to balance them. This is the one which is unbalanced. Okay, rest I think they are all balanced. Zinc sulfate, hydrogen, iron sulfate or ferrous sulfate, hydrogen. Yeah. Fine. Clear? So in this manner, we produce hydrogen gas from these metals by using dilute hydrochloric acid or by using dilute sulfuric acid. Correct? Got the point? Fine. Now, moving ahead, you would be having questions are like dilute hydrochloric acid and dilute sulfuric acid. Why are we not using dilute nitric acid? Why not dilute nitric acid? So this is a very valid question and very interesting question. See, dilute nitric acid is like a powerful oxidizing agent, which means that it oxidizes, okay, the metals. Now, what do you mean by oxidizes the metal? Just now, before some time, when we were studying Bosch process, I have explained you what is reduction, okay? And again, we are going to see it in details at the end. But still, oxidation means you can just correlate here as the process in which the oxygen is added. Fine. So here, dilute nitric acid, like it adds up oxygen in metal. Fine. Adds up oxygen. Okay, sorry, it adds up oxygen, but sorry, not in the metals, it adds up oxygen in our hydrogen, which would be formed, okay, which would get formed. But since dilute nitric acid adds up oxygen in hydrogen, what would result? Water. Correct. Because whatever hydrogen which would be formed, if dilute nitric acid is used, it adds up oxygen in our hydrogen. So instead of we getting hydrogen, we would get water. And what's the use of water to us, man? We are trying to prepare hydrogen. Correct. So no use of water here. This means that our purpose of carrying out this reaction is like not valid. Okay, why are we carrying out this reaction then? If we are not getting hydrogen, then why are we carrying out this reaction? Fine, we are carrying out this reaction, means we are actually trying to prepare hydrogen here. Correct. If you are not getting hydrogen, there is no point in carrying out the reaction by using dilute nitric acid. Clear? So for example, let me explain you. For example, suppose I take suppose zinc. Okay, not copper. For example, I take zinc. Fine. And I treat it with dilute nitric acid. So what would form here is zinc nitrate would be formed. Okay, so here zinc nitrate's formula would be like this, Zn2 plus. Okay, so 2 would go here down, and then NO3 1 minus 1 would come here. Okay, so ZnNO3, and along with it, okay, it would result into formation of water and NO2. Okay, now this dilute nitric acid, okay, it depends. If we are using cold dilute nitric acid, then we would get NO. If we are using hot dilute nitric acid, then we would get NO2. So that's the another story, but no need to go into that much details. For now, you just remember, you can just observe here, we get a nitrate. Okay, we are getting some nitrogen oxide, maybe it is monoxide or dioxide, no need to worry about that here. But you can see here the hydrogen which would get formed, okay. But now that hydrogen is combined with oxygen here, okay. This nitric acid is putting up oxygen to this hydrogen, making it as water, okay. So whatever we are getting here is not hydrogen but water. No use, right, of carrying out the reaction with dilute nitric acid. That's the reason we don't use dilute nitric acid to carry out the reaction along with these metals. Fine, understood the point? Okay. Now, one more very interesting thing is, why don't we use other metals like lead? Okay, that would be a valid question. Why don't we use lead, for example? So here a very interesting story comes up with the lead. What happens is, lead, when it reacts with sulfuric acid, or suppose you are saying as hydrochloric acid, okay, it results into formation of lead sulfate and lead chloride. This two compounds are formed. Okay, similarly, same like that of all the other metals. So they're sulfates or they're chlorides. But what happens is, when they react, okay, suppose this is a lead block, I'm putting it into in the dilute sulfuric acid. Okay, I have just, okay, dipped this lead block in the dilute sulfuric acid. Suppose, for example, what happens is, in this dilute sulfuric acid or in this sulfuric acid, okay, after dipping the lead block, this lead would form lead sulfate coating over itself. Okay, And this lead sulfate coating, oh my god, this is insoluble. Okay, so what would happen is inner lead would remain protected. Okay, inner lead metal would get protected because of this outer lead sulfate coating. Or suppose if I have taken hydrochloric acid, then it would have been lead chloride coating. Okay, and this insoluble coating of sulfate or chloride, okay, protects our lead and the further reaction doesn't take place. Okay, yes, so here very much interesting, one more interesting thing is, as I have told you that metals are not treated with dilute nitric acid, but okay, there are two metals which can react with very dilute nitric acid. Okay, very dilute nitric acid. Which are those two metals? Let's see. Okay, so these two metals, you would say that, oh man, these two metals are very unique in nature, right? Because they can react, and not only they can react, but yeah, all the metals can, means like the metals like zinc, okay, the zinc was also able to react, okay, but the problem was it wasn't able to react with dilute nitric acid and produce hydrogen. But there are two metals which can react with very dilute nitric acid and can produce hydrogen gas. Which are those two? Magnesium and manganese. So like we can say how the TV show anchors say, presenting magnesium and manganese. In that manner only they are special, man. So special because they react with our dilute, very dilute nitric acids. Okay, now here I have written already very dilute nitric acid, so I'm not going to write it again here. And they form the same thing. How the other metals were reacting with dilute sulfuric acids and dilute hydrochloric acid and producing sulfates or chlorides, these two metals would produce nitrates. Okay, magnesium nitrate. So MgNO3 twice, MnNO3 twice. Fine. Okay, Mg2 plus, so it would go here and then 1 minus would come here. Fine. So same way, MgNO3 twice in the similar manner, MnNO3 twice. Fine. And they would result into the formation of hydrogen gas. So these two we can use, yeah, but one very much interesting thing, or one thing, like here we can use dilute hydrochloric acid or dilute sulfuric acid, okay, but here whenever we are using like dilute sulfuric acid and dilute hydrochloric acid and treating it with lead, it would result into formation of the sulfates and chlorides. But one thing I missed to tell you that, yeah, initially when this would form, obviously the lead is reacting with sulfuric acid and it is forming lead sulfate, so somewhat hydrogen would be evolved, okay, somewhat hydrogen gas would be evolved. Fine, but what's the problem here is, okay, here also somewhat hydrogen gas would be evolved initially, but what's the problem is, whenever the coating would form, okay, around the metal, that coating would protect the inner lead from further reaction, right? So inner lead won't react further with sulfuric acid or hydrochloric acid, and then the reaction of production of hydrogen would stop. That's the reason we don't use lead. Understood? So though it gives us hydrogen initially, but later on it doesn't give us because of this insoluble coating. Now insoluble in terms of whom? In terms of this sulfuric acid and hydrochloric acid. So this is not soluble, the coating, lead sulfate and lead chloride is not soluble in sulfuric acid or hydrochloric acid respectively. Okay, so lead sulfate is not soluble in sulfuric acid, lead chloride is not soluble in hydrochloric acid. So due to this insoluble nature, they remain stick to the lead and they don't allow the inner lead to further react and further produce hydrogen gas. That's why we won't use these two things. Clear with this point? And now, very interesting thing. You would say, sir, you told us the reaction of magnesium, aluminium, zinc and iron to us, okay, with whom? Dilute sulfuric acid and dilute hydrochloric acids, okay, and why don't they react, and why don't we use those metals to treat, or why don't we use these metals, magnesium, aluminum, zinc, iron, with dilute nitric acid? Okay, that also you got, I hope it would be clear to you. And why we don't use lead along with dilute sulfuric acid and dilute hydrochloric acid, that also would be clear. But one question should arise in your mind, sir, what about potassium, what about sodium, right? And what about calcium? Okay, what about these three elements? Why haven't we discussed their reactions with dilute acids? Why so? Now, do you remember the first reactions which were studying, okay, in the previous video, were the reactions of potassium, sodium and calcium with even cold water. So they were like so much willing to react that they are like ready to even react with cold water. Now, imagine if they are ready to react with that cold water, won't be they ready to react with dilute acids? Now you would think, sir, oh yes, they would be like very much ready to react with dilute acids. Not very much. They are like too much ready to react with the dilute acids, and due to their too much readiness, okay, they are reacting with the dilute acids very violently. Fine. And because of such violent reactions, okay, means the reactions would be quite explosive as well. So that's the reason we don't treat these metals, potassium, sodium, calcium, with these dilute acids, dilute hydrochloric acid and dilute sulfuric acid, okay, because the reactions are too violent and too explosive. Okay, so forget about producing hydrogen. Since they are too violent and explosive, it is not feasible to carry out them. Understood? Okay. Now what is the meaning of feasibility? Means it is not like of our use to carry out the reaction. Okay, there won't be we not of our use, but we can say that feasibility simply means that it is not possible to carry those reactions. Okay, the possibility is means not favorable. Fine, or you can say favorable. Feasible means favorable, so it is not favorable to carry those reactions. Okay, so now let's quickly see one question before ending the video, which is, now see, you have to just recollect whatever we have studied to answer this question. Okay, one very interesting thing you have to recollect and you would get the answer. So what is the question? Which of the following metal, okay, does not give hydrogen, fine, with dilute sulfuric acid? It simply means that it won't react with dilute sulfuric acid, because we know metals react with the dilute sulfuric acid and they give us metal sulfates. I'm just writing MS. Okay, metal sulfates and hydrogen gas. So they are asking us which of the following metal out of these four does not give hydrogen with the dilute sulfuric acid, So the metal which won't give hydrogen with dilute sulfuric acid means it won't even react with dilute sulfuric acid. Correct? Means simply it won't even react with dilute sulfuric acid to give the products. So if there are no products, no hydrogen, right? So does not give hydrogen with dilute sulfuric acid, which simply means the metal which does not react with dilute sulfuric acid. Now, which of the following four metals does not react with dilute sulfuric acid? Come on, quickly think over and get to the answer. Okay, so I hope you would have answered it right? If you would have paused and resumed back, you would have answered it right, thinking that those metals which are below hydrogen in the activity series, like copper or like mercury, silver, gold, won't react with dilute sulfuric acid, because we have learned the metals above hydrogen in the activity series would react with dilute sulfuric acid, resulting into the formation of metal sulfates and hydrogen gas. Okay, now the metals which won't react with dilute sulfuric acid we have to find out. So the metals which won't react with dilute sulfuric acid are those which are below hydrogen in the activity series. Now copper is a metal which is below hydrogen in the activity series. Apart from copper, mercury, silver, gold, CuHg, AgAu, these are the four elements. Platinum is also the element which is below hydrogen in the activity series. So out of these five elements, means these five elements won't react with dilute sulfuric acid, but other than those five elements, okay, the elements which are above the activity series, like for example starting from potassium, then coming to sodium, then calcium, magnesium, then aluminium, right? And after aluminium, okay, so see, potassium, sodium going up, calcium, magnesium going up, and then going to the right, okay, right here, after magnesium, aluminium, okay, and from aluminium then zinc, iron, nickel, right, tin, lead. So skipping tin and nickel, Okay, coming back to lead. So zinc, iron, nickel, tin, lead, hydrogen, and all these things. So this is the activity series. Now you can see simply iron, zinc, and magnesium and zinc, right? So iron, magnesium, see iron, magnesium, zinc, they are well above hydrogen in the activity series, right? Iron, magnesium, zinc. So iron, magnesium, zinc, these are all well above hydrogen in the activity series. So they would react with dilute sulfuric acid producing hydrogen gas. But copper is below hydrogen in the activity series, and that's the reason it won't react with dilute sulfuric acid. Okay, so it won't also be able to give hydrogen, correct? So friends, with this we have reached the end of this video, and I hope you would have enjoyed learning with me. You would have understood the concepts which we have learned so far. And as you all know, Learnohub matlab free है पर best है. So see you in the next video with the remaining concepts of this chapter. Till then, you keep studying, take care, bye bye, and have a great day.